Hi, this video is going to be on series. Series is a sum of values, and so you could think of it as a sum of the terms in a sequence. So remember, a sequence in the previous video is just a list of values, and a series is the sum of those values. There are some things that you could do with series and special types of series. One test that you might do is called the test for divergence, and this can be used in order to determine whether a series diverges or not. It does not determine convergence, so either you have evidence that it diverges or you didn't learn anything from this particular test. Some special series, you've got the geometric series, which will take this form here, and r is it could be any value, but if it happens to be a fraction or a number between plus and minus 1, then the series will converge, so it's good to be aware of that. Otherwise it diverges, so depending on the r value, you do know whether it diverges or converges. A telescoping sum type series is one where if you expand that series out and you write the values that you're adding, some will subtract out and you're really just left with a few finite terms, and you'll see an example of that shortly. And a harmonic series has a form like the sum of 1 over I, where you're adding up smaller and smaller terms. And so it's good to be aware of that. A harmonic series diverges, and there's a proof here showing that it diverges, but I will leave that to you to look at on the side. It's kind of a neat, not necessarily intuitive proof, but it's cool how it works out. So let's get to some of these examples. The first one is to write out a list of values in the series that are given here. And so for the first one, we're summing n from 1 to infinity. And so when n is 1, we've got 1. When it's 2, we add 2. When it's 3, we add 3, and so forth. And so the series is 1 plus 2 plus 3 plus 4 onwards. And so this is an infinite series that's just getting bigger and bigger and bigger. It's clearly not going to converge, but we're going to show that in number 2. And part B, you have the sequence cosine n pi over 6, and you're doing n from 0 to 6. When it's 0, you've got 1, then plus root 3 over 2, plus 1/2, plus 0, then minus 1/2, minus root 3 over 2, minus 1, and that is when n is 0, 1, 2, 3, 4, 5, 6. So those are all the terms which you could visually inspect and recognize that you are adding and subtracting the same values, and that this sum is 0. Let me go back and just talk for a moment a little bit more about part A. If A had, let's say, been a finite series, and let's say it was 1 plus 2 plus 3 plus 4 up through n, then this, I had been taught a long time ago, the sum is equal to the blind snail formula, and that formula is n over 2 times a plus l. The blind snail, because you've got the sum s, n, a, l, so you have the word snail without any i's. Haha, I know. But obviously, if you think that's corny or funny, it'll probably make it easier for you to remember it. And so the blind Snell formula is used for a sum like this, where A corresponds to the first term in the sequence, and L will be your last term. And so in particular for us, we have n over 2, and the first term is 1, and the last term is n. And so whether you write n plus 1 or 1 plus n, that doesn't matter, but that would be the formula that you would use in order to figure out the sum of this finite series. If it were finite, it isn't. All right, but let's move on to number 2. So in 2, we want to determine whether series are convergent or divergent. And so intuitively, like I had mentioned before, we know that the series of sum of n from 1 to infinity, is going to explode because you're just adding larger and larger terms. But to actually prove it, we could recognize that an is n, and the limit as n goes to infinity of n is infinity. And according to the test for divergence, we have that if the limit of the sequence does not exist or is finite L, which in our case we have the infinity symbol that falls into the does not exist group, now we know that the series diverges. And so we know that sum as n goes from 1 to infinity of n diverges by the test for divergence. And then B, we have a series, and this is a series is given without a summation sign, and so this is just a fixed type of series. And so this one we could get directly by finding the limit behavior as n goes to infinity of Sn, and Sn is what is given there. So that's 2n over 3n plus 5. And on top and bottom, you have infinity over infinity, which should make you think of L'Hopital's. And when you apply that, you have 2 on top, 3 on bottom, and the limit of a constant is 2/3. And since this is finite, we know that Sn converges. And moving on to number 3, we want to find the sum of the geometric series 5 minus 10/3 plus 20/9 minus 40 over 27 plus onwards. And so you could tell that it's alternating, and we just need to figure out, well, what is the common multiplier here? What's going on? So when I look at this, I realize, okay, well, to get from 5 to negative 10/3, I had to multiply by negative 2/3. And to get from negative 10/3 to 20 over 9, if I multiply that by negative 2/3, that would work. And to get from 20 over 9 multiplied by negative 2/3, that would give me negative 40 over 27, which is the fourth term. And so I could tell that the R, the common ratio, must be negative 2/3. And for an infinite geometric series, and just to demonstrate it, and so here, if we have just your general geometric series 1 plus r squared plus r cubed, and I'll treat it as infinite, a trick to figure out what that sum is equal to is to multiply it by the common ratio. So that's going to give us r plus r squared plus r cubed onwards. And then to subtract the second row from the first. And so we've got s minus rs. And on the right side, we have 1, and that's it, because r cancels out with r squared with r squared, r cubed with r cubed, and all subsequent terms disappear. And when you solve for s, you get s is 1 over 1 minus r. Now this is handy because we want to know the sum of this particular infinite sequence. And now that we know the formula for it, we have s is 1 over 1 minus negative 2/3, which is 1 over 1 plus 2/3, or that is going to be 5/3, which is the reciprocal of 3/5. And so that is our sum here, but it's not quite done because this would be the sum if our this is the sum of 1 minus 2/3 plus 4/9 minus 8/27 and so forth. But what differs from this and what we have is that our original series is multiplied by 5, which means that this sum, I'll call this sum 2 and the first one sum 1, is equal to 5 times sum 1. So we have 5 times 3/5, which is 3. And so it's important to keep in mind that when we did our derivation of 1 over 1 minus r, our geometric series began with 1. So whenever you're dealing with a geometric series, make sure that you factor out what you need to in order to have the first term as 1. And then don't forget to multiply your answer by that in the very end. All right, so just to be clear, our answer is 3. Number 4, we want to know, is the series the sum of 2 to the 2n, 3 to the 1 minus n convergent? So this could be a little hard to deduce exactly what its behavior is, but I'm going to make some manipulations. I'm just going to focus on the inside, and I recognize that 2 to the 2n, 3 to the 1 minus n, I could write a little differently. I could write that as 2 squared to the nth power times 3 times 3 to the negative n. 2 squared is 4 to the n times 3, and 3 to the negative n is 1 over 3 to the n, which is 3 times 4/3 to the nth power. And so this is useful because the summation we now know is equal to the sum as n goes from 1 to infinity of 3 times 4/3 to the nth power. And this is a geometric series. With r of 4/3, which notice that is greater than 1. And that's important because remember back here when I introduced the geometric series, I pointed out that if r is equal to or between plus and minus 1, then it's convergent, otherwise it diverges. And so since our r value is outside of that interval from plus or minus 1, we know that the series diverges. And that is just a collection of some things that you can do with series.